Alright, we're back again. Physics 212 Practice Exam 2, problem number 11. The question is, in the circuit shown in the figure, if voltage source, right here is 25 volts, what is the equivalent resistance? Alright, so that's part A. And it's important when trying to find equivalent resistance to analyze your circuit and see what parts of it are parallel and what parts are series. As we can see, going from here to there was only one choice. We could only flow through here. But when we hit this junction, we have a choice to split. And then we come back together at this junction and have no choice from here to there. So this part of the series is circuit. This part of the circuit is series, this part is series, and these two components are parallel. Now the way I always like to think of collapsing the circuits is to think of them like an accordion. And so I'm going to take my parallels and combine them into a series equivalent. And then now I would have 3 series resistors. I can add those linearly. So let's go ahead and give that a go. So we know that 1 over R, this is how we add parallel. 1 over R23, that's what I'm calling the equivalent resistor of when we combine R2 and R3. So 1 over that equivalent is equal to 1 over R2 plus 1 over R3, which happens to equal to 1 over R2 is 20 ohms, plus 1 over R3 is also 20 ohms. So that gives us 220 equals 1 over R3. We could inverse this and we'll end up with the equivalent resistor combining R2 and 3 is going to equal to 20 over 2, which is 10 ohms. I don't know why I put an approximate there. That's exactly 10 ohms. Alright, so now essentially what we've done is we've drawn a new circuit. Same voltage source, same resistor 1, same resistor 4, but now we've combined R23 as 10 ohms instead of having to deal with them separately as 20 ohms apiece. And so we know that we can now add these resistances linearly to get a circuit with only one equivalent resistor. So now we're going to combine all these into one resistor by using the fact that R1, 2, 3, 4, you could call this R total. That's the combination of all the resistors to an equivalent resistor. It's going to equal to R1 plus the equivalent R23 series resistor plus R4. And we can go ahead and plug all those into our calculator. So we've got R1 is 10 ohms, plus R23 is 10 ohms, plus R4 is 30 ohms. And so we're ending up with a total resistance of an equivalent circuit as being a 50 ohm resistor. So there is part A, which states that the equivalent resistor for this circuit, this combination circuit, it's not series, it's not parallel, it's combination, is equal to 50 ohms. Alright, part B, what is the power across R2? Okay, so there's multiple ways to calculate power. Let me keep this equivalent resistance up there. So the different ways to calculate power are as follows. We start with knowing that power is equal to current times voltage. And then we can go ahead and use Ohm's law, which states that V equals I times R. You'll see I could substitute V in here as I times R. So that would give me P equals I squared R. Or I could divide R over here and get I equals V over R. Substitute that in for I, and I could get P equals V squared over R. So those are kind of the main tools for a DC circuit series parallel combination. These should get you what you need. The important thing to remember is that when we go across a resistor in series, there is an associated voltage drop with that. So what I mean is if the voltage is 25 volts here, by the time we get to here, we will have lost some voltage. But the current will be the same across the resistor. The current will, because electrons have to flow at the same rate if they're only on one path. So in other words, in electronics, there are no traffic jams. But when we get to the parallel circuit, the electron stream has a choice. It can go right or left. So now we have two currents. What's interesting here, though, is that the voltage drop across R3 and R2 is both. It's the same across both. So even though the current splits, the voltage stays the same, whereas here the voltage drops, but the current stays the same. Then we get back to series, and the current stays the same, but we have an associated voltage drop. So to work our way over, because we're curious about the power through, here it is. We're curious about the power through R2, which is one of the parallel terms. So the first thing we're going to need to do is draw that equivalent circuit again. And so if you'll remember, the equivalent circuit combined the parallel into one resistor. We called it R23, which was approximately, I don't remember, we may have to recalculate it. R1 is 10 ohms, R2, or this is R4, I'm sorry. R4 is 30 ohms. And if I remember, they added up to 50, so I'm going to go ahead and say that R23 was exactly 10 ohms. Alright, so what we need to do is calculate the voltage drop across these resistors. So if the source is 25 volts, then we know that the sum of voltage drops, so in other words, VD1 plus VD2, those are voltage drops, plus VD3, or I'll call it VD4 and this VD23, because it's over resistor 2,3. That has to equal the voltage source, which is 25 volts. And so one of the ways we can solve this is we can say that V equals I times R. We've got our total resistance of 50 ohms, times I equals our total voltage is 25. So we can now solve for the current flowing through every point on this equivalent series circuit. So 25 divided by 50 is 0.5. So our total current is 0.5 amps. Alright, so now that we know that, we can go to each one of these resistors individually. If you're curious about what the voltage drop across R23 is, we can say that the voltage drop across R23 is going to equal the current across R23 times the resistor value R23. So it's just Ohm's law, but it's specific for resistor 2,3. This time we don't know the voltage drop across here. We do know the total voltage, but not the voltage drop. We do know the current, because the current through this equivalent circuit is the same everywhere. So we know that's 0.5 amps. We know the resistor value of 2,3 is 10 ohms. So that's going to be our voltage drop across resistor 2,3. And of course that's going to come out to be 5. So in other words, the voltage drop, it's getting a little messy, across 2,3 equals 5 volts. Now I'm going to go ahead and erase again. So we could solve for current. We could solve for current and use this equation, but it's actually going to be easier just to use the voltage. And so we calculated the voltage drop across R2 and 3 as a combined circuit, and so that means the voltage across R2 is going to be the same as the voltage across R3. So if we're looking for R2, we can use the formula that power equals V squared over R, the one we derived here. We know the voltage drop across resistor 2 is the same as the drop across both resistor 2 and 3. So that's 5 volts. So we've got 5 volts squared divided by the resistor value R2, which is 20 ohms. And so let's see what we get. We get 25 over 20. That's 1.25. This power, this resistor is dissipating 1.25 watts, which is actually kind of a large amount of power to be dissipated from a resistor. Most resistors you'd see in a breadboard dissipate quarter to a half watt. So this is going to be a little bit bigger of a resistor. I hope this was helpful. And know you can solve it using current, but it's going to be easier to solve it using the voltage drop. I hope this helped, and have a great day.